Hello, everyone. I'm Diego Souza from NEMPE, the Brazilian National Institute for Space Research. And with my colleague Marcial Garbanzo from the University of Costa Rica, we will present how to visualize and analyze GOES-R data using Google Colab. And in this first part of the presentation, we will quickly review some of the satellite data access mechanisms, some data processing aspects. We will introduce Google Colab, what it is and how it works, show some GOES-R data processing examples, and share additional resources for your future reference. Let's begin. One of the biggest improvements of the current generation of satellites is the variety of mechanisms available for accessing data. On the left, you have some of these mechanisms. Users may, for example, have antennas pointed towards GO16 and receive data directly from the satellite. Also, one possibility is retrieving near real-time data directly from the cloud. And that's what we are going to see today. NOAA provides these datasets in a format that can be processed according to the user's needs. Unfortunately, there are open source tools freely available to process this data, and Python is one of these options. On the right, we have a Go16 ABI full disk RGB composite created with Python and some of the libraries that are available that could be used to process and visualize GOES-R data. And Python is available for free. It's easy to start programming, as we're going to see today. The learning curve is considerable but very gradual. And one of the things that I like the most is that the community is very, very active. When I have any problems and send a question in the user forums, usually the same day I have an answer. Also, there are many, many modules and libraries available for various satellites and sensors, and it supports different data formats, such as NetCDF, the format that we will explore today. And Python works on different operating systems. It's not difficult to integrate Python with other software and applications. It's very common to find softwares that has a Python module like Makaidas V, Quantum GIS, and many others. Another interesting fact is that we have conducted a survey last year through the WMO Satellite Data Requirements Group, which Marcial and I are co-chairs, and we had more than 200 responses from more than 30 countries. And among the questions, we had a specific question about data processing. And as you can see here, by far, Python is the most used tool by the satellite data user community. For both geostationary satellites in blue and low Earth orbit satellites in orange. But what can you do with Python? As a motivation, let's see some examples very quickly. You can process GOES-R ABI images and create very nice animations. You can process data from the Geostationary Lightning Mapper or GLM. You can process and visualize GOES-R derived products. And there are more than 30 derived products available for free in the cloud. In this example, we have the derived motion winds, for example. Not only data from GOES-R, you can process data from other geosatellites as well. In this example, I have created an animation covering the whole globe, processing data from GOES East, GOES West, Meteosat 0 degree, Meteosat 45.5 degrees, and Himawari 8. You can also process imagery and products from LEO satellites. And here we have some examples, such as NOAA 20, GCOM, and METOP. And if you want to create images with very high resolution, you can also use Python for that. Here we have composites from the Sentinel satellites, also created with Python and the SatPy library. The image on the left is from Sentinel-2, and the image on the right is from Sentinel-3. The image on the left has 10-meter resolution. Very impressive. You can also process oceanography products like sea surface temperature, chlorophyll, altimetry data, anomalies, and much more. We have created these plots for our training here in Brazil, processing files that are freely available from the open FTP servers provided by NOAA. And if you want to process outputs from numerical weather prediction data, GFS in this case, you can also use Python for that, right? And here we are overlaying some analysis with GOES-R imagery. And these are some examples from a training we have organized a couple of years ago here in Brazil. Also, it is also possible to process data from weather radars. And for the US, we have data available for free in the cloud. And it is totally possible to create many derived products with Python. And here we have some examples that we are preparing for an upcoming training here in Brazil. In the end, everything is possible. You may create any kind of graph you want using matplotlib and other scientific calculation libraries that are available. Here we have some plots we have prepared for our training in radiation products, like the trajectory of the sun, which is a 3D graph, or the Wien's displacement law. With a programming language like Python, you have total control of your data. And that's what we are going to see today. But how can we run Python scripts? We have basically two ways to do that. Running scripts locally in your own computers and servers, or running scripts directly in the cloud, as we are going to see. If you want to run Python scripts in your computers, you need to install some tools, like Conda, for example, to be able to install and manage Python libraries. You will also need a text editor or an IDE, an integrated development environment, to write and run your code. And you will also need some sample imagery, and there is a variety of mechanisms available. We are not going to cover how to do this in this demonstration, but we will provide some links at the end with the necessary procedures. Running scripts locally is useful when you need to generate images operationally for your web pages, for example, or downstream users. On the other hand, to run Python scripts directly in the cloud, you only need a so-called online notebook. And in this demonstration, you will learn how to process GOES-R data in the cloud using Google Colab. We have prepared some examples that are ready for use. For this first demonstration, at this link, you can access the short version of this notebook with some basic operation. But in the end of this presentation, we will provide another link with the longer version, with many more examples for your future reference. The free version of Google Colab basically provides a Linux virtual machine with Ubuntu installed, 13 GB RAM, approximately 100 GB of storage, and Python already installed. The only thing you need to create, edit, and save your scripts is a Gmail account, so you are able to manage your Colab notebooks using your own Google Drive. Let me quickly show how it works. If you click at this link here and select New Notebook, you will see this. This is a blank notebook, okay? And by default, it's called untitled 0.ypynb, which is the extension for Jupyter Notebooks. So this is basically an online Jupyter Notebook. Also, you are able to insert code cells like this one, where you may write your own code, like this, for example. Let's see, A is equal to 1, B is equal to 1, C is equal to A plus B. Let's print the result. Print parenthesis, the value of C is column, comma, C, and run the code cell by clicking on the play button. Sorry, I forgot a comma. And you got the nice thing is that when you got an error, you see the error right away. Put the comma under right after my string, and that's not correct. You have to put after your string. So this is how this Jupyter is called the Colab notebooks shows the errors, right? So this is a code cell, okay? And apart from code cells, we may create text cells with some instructions or a description of your code, like this. By clicking at the plus text button, we add a new text cell, right? And you are able to move it like this. And if you double click at it, you can insert your text like this. Welcome to the Goals Are DataJam competition. Let me make it bold and increase the size of the text. And this is it. Okay, so this is basically a Colab notebook, right? We are running Python code directly in the cloud using a Linux virtual machine provided by Google. Okay, but don't worry, we will not need to create a Colab notebook from zero to start exploring Gozar data. We have already created some notebooks for you. And that's the benefit of these online tools. You may create your notebooks, share it with your colleagues or other developers, and add them, sorry, as contributors. And they will be able to change it, add their own code. And in this example, I have shared this notebook with you, configured as readers only. Okay, so you will not be able to change it or save your edits unless you create a copy of this notebook in your own Google Drive. And that's what we are going to see now. Let's see some basic instructions and useful hints. The first thing we need to do is creating a copy by clicking at File and Save a Copy in Drive. This will open another tab with a copy that is stored in your own Google Drive. You may change the name of the notebook the way you want. In my case, for example, I have also created a copy because I do not want to make changes and affect the original notebook. So I have just my name here, Diego, underline the original name. So this is already a copy that I have created for myself. Okay. Um, and to run code cells, you just need to click at the play button on the upper left side of each code cell. A nice shortcut for running code cells is Control and Enter. I use it a lot because when your code cell gets bigger, you don't need to scroll up in order to click the play button. Okay? And as we have seen, it is possible to create code cells and text cells, either by clicking on the buttons on the upper part of the interface, or if you move your mouse button, your mouse pointer between two existing cells, a couple of buttons will pop up, and you are also able to create a code or text cells. Another detail, commands starting with an exclamation mark, like this one here and here, these are Linux shell commands. All the other commands, like these commands here or this print message here, these are all Python instructions. Also, on the left side of the interface, you may visualize the table of contents, okay? With the contents created by you or the developer who shared the notebook with you. Also, when you run a code cell, you see that the output of the instructions will appear below the code cells. And these are the outputs. And if you want to clear all the outputs from your notebook, and this could be very useful sometimes during development. Just click at Edit, clear all outputs. Also, it's possible to restart the Python runtime. At runtime, restart runtime. And by doing that, all the Python variables will be reset. That could also be useful during the development of a new algorithm. But if you want to, apart from resetting the variables, completely resets the virtual machine to its initial state, just click at runtime and disconnect and delete runtime. All your notebook instructions will be kept. However, all the libraries you have will be deleted. And talking about resetting the machine, the Colab notebook will automatically reset itself if you stay a long time without using it. And finally, as we have seen, by clicking at the three lines here, you can see the table of contents. However, if you click at this folder here, you will view the virtual machine directories like this. And the Google Colab default working directory is called content slash content. Okay? All the files that we will download or create will be there. And the final detail is that if you want to manually upload your own files to the Colab notebook, just click at this icon here. And that could be very useful because you would be able to manipulate your local files using the Colab's virtual machine. I'm sorry. Okay, now let's begin to explore the short version of the Colab notebook that we have prepared for this demonstration. Just remember, after clicking at this link, you must create a copy of this notebook so you are able to edit it and save your changes. Okay, let me open my copy, and this is it. Here I have the table of contents on the left side. After some introduction, we have our first code cell where we will install the required Python libraries and download some Go16 imagery samples from the cloud, from the Amazon Cloud Services in this case. Please note that almost all instructions in this code cell starts with an exclamation mark, like here, here, and here, meaning that these are shell commands. So we are basically using pip, the Python package installer, to install the required libraries that we will use to process GOZAR data. Because by default, Python is installed only with some basic libraries. First, we will install the netcdf4 library, so we are able to read the pixel values from a GOZAR image in netcdf format. Then we will install Cartopy, which we will use to overlay maps with our GOZAR plots. Then, with the mkdir command, we will create a folder called samples, where we will store the GOZAR files. And finally, we will use the wget command to download samples from the cloud. We will download a sample of the band 13, as you see here, the 10.3 micron band covering the full disk, which is available every 3 minutes. We will also download a sample of the channel 2, the 0.64 micron band covering Conos, which is available every 5 minutes, and a third sample of the same channel, channel 2, covering one of the mesoscale sectors, which are available every minute or every 30 seconds, depending on the event. So that's what we do in our first code cell. And here with the key parameter, we just specify where we want these samples to be downloaded at content slash samples in our virtual machine. Okay. An interesting question is, how do we know these links? Which links we should use to download data from Amazon, for example, right? And in this case, we have used a very nice graphical interface developed by Brian Blaylock from the University of Utah. And here it is, right? Um, in this interface, let me reload it here. In this interface, you may select the satellite, okay, Go 16, Go 17, or Go 18, the domain, full disk, conus, or mesoscales, the product. Look at the amount of product apart from the ABI images, GLM files. Look at the amount of derived products that you may download. The date and the hour, and if you click at submit, you will see some timestamps for each one of the 16 ABI bands. And if you, for example, right click at it and select copy link address, you have this. Let me paste it here for you to see. And this is the link from the Amazon Web Services that will download this file for this band, for this hour and date, for this product, for this domain, for this satellite. If, for example, I copy and paste this link in my browser, you see it is downloading the image to my computer, but I want to download it to the Google Colab virtual machines, and that's what we are doing here. Okay, okay, let's see our next cell. Next, we have the text cell, and in text cells, we may have images as well. And we have inserted a reference table with all the 16 ABI bands, the wavelengths, resolutions, spectral range, and nickname. And when you are dealing with multiple bands or building RGB composites and doing some calculations between bands at channel differences, etc., it's very useful to have a reference table. So you have them here, okay? So you may copy this text cell and paste it in your own notebooks, for example. All right, now let's import some libraries. In our next code cell, we import all the libraries needed for the instructions used in this demonstration notebook. First, we will import the netcdf4 library for reading the pixel values of our images. Then we import the matplotlib library to create our plots, and we will import it as PLT. We have called it PLT, but you may call it any way you want, as long as you refer to the same name in the rest of your code. We also import the datetime library to read and format the ABI acquisition time. We import Cartopy to add maps to our plots, and we import it as CCRS, which stands for Cartopy Coordinate Reference System. But again, you may call it any way you want. And we also import NumPy to make some calculations as needed, right? Remember all those libraries from the first slides? You can import any of them as long as you install them, okay? Let me just run this code cell here. All right. A green check mark means that the code cell has been successfully executed. Um, and in our next code cell, we will open a Go16 ABI file with the dataset command from the netcdf4 library. And we need to indicate where the file is located. In our case, inside the samples directory that we have created in the first step. And this is the file name, okay? And this is the file name convention for a GoZAR image, right? First, we have OR for operational system real-time data, ABI, which is the sensor, okay? L2, which is the level. This is a level 2 file, meaning that these files already have the pixel values in brightness temperatures if you are manipulating IR channels, or reflectance factors if you are dealing with visible bands. Then we have the product name, CMIPF, or Cloud and Moisture Imagery Product Full Disk, as NOAA calls it. The scanning mode, mode 6 in this case, which is a full disk image every 10 minutes. The channel, channel 13. The satellite, go 16. And three timestamps. The start of the scan, the end of the scan, and the file creation date, right? When the ABI sensor started scanning the full disk, when it ended, and when NOAA created this file, these NetCDF files in their servers, right? And we have 4 digits for year, 3 digits for the Julian day, 241 in this example, and then the hour, 15 UTC, 20 seconds, right? And please note that the time difference between the start of the scan and the end of the scan is approximately 10 minutes, 9 minutes, 52 seconds. And that's because we are working with a full disk file, which takes 10 minutes for a full scan. Okay? Okay. And please note that NOAA took 6 seconds, 52 to 58, to generate this image, which is quite impressive. So with that, we create an object called file. You may call it any way you want, but in this example, we will call it simply file. And one of the nice things about NetCDF files is that you have many data sets inside this file, right? Which the data provider, NOAA in this case, they add some useful information about the data, which is called the metadata. That is, information about the information. And apart from the image itself, we have, for example, information about the time, date, projection, data quality flags, and much, much more. Just look at this huge list of information, and all of that in our .cdf file, right? And with this command here, variables.keys parentheses, you can list all the variables available in a netcdf file, right? And according to the documentation of this product that you may find at this link, right? The data set that contains the brightness temperatures or reflectance factors, if you're dealing with the visible bands, it's called the CMI dataset or the cloud and moisture imagery dataset. This one here. So that's the dataset we need to process and read. Okay, let me run these cells. Okay. All right, now let's check the characteristics of the CMI dataset. And that's what we are going to do in our next code cell. Um, in this code cell, we specify that we want to check the characteristics of a particular dataset with the file.variables command. And the dataset name under brackets, CMI in this case. And as you may see in the output, this particular image, it has 5,424 rows by 5,424 columns, and the unit is Kelvin. We have much, much more information about it, but for now, let's consider only this, okay? Um, Here. Now that we know the characteristics of the CMI dataset, what I'm doing here is reading the pixel values, right? Let's read the pixel values and plot that information. Here, I'm creating a variable called data. You may call it any way you want as long as you refer to it in the rest of your code, right? I specify the data set I want to read, CMI in this case, and a column inside brackets. With this, I say that I want to read the whole 2D array, all the 5,424 rows and all the 5,424 columns, right? This whole array of this data set. Also, in the same instruction, I'm converting from Kelvin to degrees Celsius by subtracting 273.15. Please note that at this point, you may manipulate the pixel values any way you want. And in this example, we are simply subtracting just for demonstration purposes, but you can make any calculation you want. You have total control of your data. And after that, right, now that I have a variable with all the brightness temperatures, let us plot it. And before that, I need to configure the plot or how I want to show this information. And the first thing I do is selecting the plot size with the fixed size parameter of the figure command of the matplotlib library. So by default, we specify the size, right, as the width and height in inches. So in this example, we will create a 20 by 20 inches plot. And finally, we show the image with the imshow command from the matplotlib. And we need to pass some parameters as you are seeing here. In this case, the data or the variable we want to plot. So we are plotting the variable data, which is a 2D array, okay? The minimum value of our color scale, the maximum value of our color scale, and remember that we have converted to from Kelvin to degrees Celsius. That's why I'm using minus 80 to 40 here. And the color map we want to use and with the CMap parameter, right? And in this case, we are using the grays color map with an uppercase G and E, right? And this is a grayscale ranging from white for the lower values and black for higher values because in this example, we are going to plot an IR channel, right? So we want to see the clouds which have lower brightness temperature values as white and the surface, for example, which has a higher brightness temperatures as black, right? And you may use any color map you want and any range of values you want. And at this link here, you may find a list of the available default color maps that you may use. Let me quickly access it for you to take a look. For example, if you search in Google for Python color maps, the first result will show you a list of the available color maps, right? And this is the one we are using now called grays, from white to black. But you have dozens of options. Okay, so let me access my test notebook, read the variable, convert to Celsius, and here we have, this is the original plot. And as you may see here, right, on the y-axis, you have more than 5,000 rows, and here, more than 5,000 columns. This is the full array. That's why we have specified a column under brackets. It is also possible to visualize only part of the image if you want. Let's change the color map, for example, to jet, and run the code cell. And jet is this one here, from blue to cyan to green to yellow to orange to red. Okay? Let's see the result. And here you have your full disk and the coldest cloud top temperatures as blue, shades of blue, and the surface, which has the higher brightness temperatures in tones of red. So you have total control of your data. And if you want to read only part of the image, let's suppose I want to read only rows 0 to 2000 and columns 0 to 2000, for example. It's totally possible. So what I did here, I just specified the region I want to read as lines and columns. And this is the result. I'm just reading rows 0 to 2000 and columns 0 to 2000. Okay, let me return to the original code and run it again and run it again. Okay, now we already know how to create a basic plot, right? Now let's add some decorations. Um, and the next couple of explanations, they are a little bit difficult to understand at first, but you don't need to worry, right? Because in the end, we will be copying fragments of code that we will see and paste them in your own script, and they will simply work, okay? So the first thing I want to add is a title. And on this title, I would like to show the ABI acquisition time and date. And this is a little bit tricky, but we will get the idea. This is what I want to do. I want to add a title with the timestamp, okay? And to do that, the first thing we need to do is reading the time and date from the metadata. And there is an attribute called time covered start, which informs the start of the ABI scan. And here you see how NOAA, the data provider, how they provide this information in the metadata. 4 digits for the year, a hyphen, 2 digits for the month, a hyphen, 2 digits for the day, followed by an uppercase T, followed by 2 digits for the hour, a column, 2 digits for the minutes, a column, 2 digits for the seconds, a dot, 1 digit for the milliseconds, followed by an uppercase Z. And if you are okay with this formatting and would like to show this information this way, that's the only thing you need to do. You just need to read the information from the metadata and plot in your image. Okay? But in this example, I do not want to plot the information like that. I want to format the timestamp the way I want. And for that, I will use the datetime library, which we have imported in the first steps. And in order to create a datetime object, like this one, which I have called dateObj, I need to pass two parameters. First, the original string, which I have called dateString, right? This will have this information here. But I need to inform the library, the datetime library, how this information is formatted using some format codes from the datetime library, which is basically a percent sign followed by a letter. And each letter has a meaning, which you may find at this link here, right? All these format codes. And for example, an uppercase Y means the year with 4 digits. A lowercase y means the year with 2 digits. So I'm just saying with these format codes how NOAA formatted acquisition time. Okay? Um, and by passing the original string and how it is formatted, I may create this datetime object. And with this object, I can format this string the way I want using the same format codes as we are seeing here. So here I'm creating a custom string, which I have called date, right? Um, and I want it to format it this way, right? 4 digits for the year, 2 digits for the month, 2 digits for the day, a space, 2 digits for the hour, 2 digits for the minutes, a space, followed by UTC. And that's what you're seeing here, okay? But I could use um, any of these format codes. Let's go to Colab, okay? So here I'm reading information from the metadata, and here I'm formatting the information the way I want, right? However, here I select how I want to format it. But here, just look that I have used these format codes, uppercase A for the weekday and uppercase B for the month, for example. When I run this, you have Tuesday, August 29, 2023, 15 UTC. So with these format codes, I can format the date the way I want. Okay, so now that we have a string with the date, let's create some titles. And to create titles, we will use the matplotlib title command. I will add two titles, one located on the left and one located on the right. One located on the left and one located on the right, right? And in this example, we are passing some parameters. First, the text of the title. And in this example, go 16, band 13, 10.3 microns, and with slash m, I'm just skipping a line before printing the date, right? Go 16, band 13, 10.3 microns, I skip a line and plot the date. I want a bold font, 10 pixels for the size, located on the left. And on the right, simply goes our DataJam. Okay. Another thing I want to add is a color bar, right? To um, to show my color scale and my minimum and maximum values, my brightness temperatures, so you have a reference, okay? And to do that, we can use matplotlib's color bar command. And in this example, I'm passing some parameters like the title of the color bar, brightness temperatures, brightness temperatures, okay? Um, if I want to extend the color bar on both sides or only on the minimum or only to the maximum, and here we are extending it in both sides, like here and here, okay? The orientation of the color bar, and in this case, horizontal. With the path parameter, I'm just specifying the distance between the color bar and the main plot. And for example, with 5%, I'm saying, hey, I want this distance here to be 5% of the size of the main plot, okay? And the shrink parameter is a multiplication factor, right? It's a size multiplier. So with 75%, I'm just saying that I want the color bar with 75% of its original size, okay? Okay, now we have added a title and a color bar to our plot. Let's make some quick changes in Google Colab, right? And we can change the title any way we want. So for example, I could change band to channel. I can add, for example, goals are DataJam competition. I can change the orientation of the color bar to vertical. Okay. And let me choose another color bar. Let's use this one, rainbow, just as an example. I got an error. Let me check what the error. Oh, it's not the orientation. The orientation is vertical and the color map is rainbow. Okay. So one of the nice things of this interface that is that it shows the errors in the output cells, and you can easily check what the error is, right? So here I have my new plot, right? Channel 13, the time and date, goals are DataJam competition, and the color bar in the vertical orientation. One nice thing talking about color maps again is that if you add underscore R to the name of the color bar, we will reverse the color bar like this. Okay, so you have total control of your data and of your plot. Any aspect of the plot can be changed. And to finish this demonstration, we would like to show you how you may add maps to your GOZAR plot. And for that, we will use the Cartopy library. And to do that, we need to inform Cartopy the projection of our data. And for GOZAR, we need to use the geostationary projection. Cartopy supports dozens of projections, and you may find all of them in this link here. And for the geostationary projection, you need to pass two parameters. First, the central longitude, right, of the satellite. And GO16 is located at 75 degrees west. Fortunately, we don't need to insert this number manually because this is also available in the metadata, okay? So as the file variable command, I can read a dataset called Gauss imager projection and a sub-dataset called longitude of projection origin. And this is the central longitude of the satellite. I'm storing this value in the longitude variable and passing it as a parameter. Another parameter I need to pass is the height of the satellite, which for geostationary satellite is something above 35,000 kilometers. And we can also read this information from the metadata. On the same Gauss imager projection dataset, we have a sub-dataset called effective point height. And we pass this height as a parameter, okay? And with that, we can add some Cartopy features, right? Like country borders, coastlines, grid lines, okay? And in this case, I'm setting all three as black, right? Coastlines as black, country borders as black, and grid lines as black. And I can also configure the line widths for each one of these map elements, as you see here. However, there is one more parameter I need to inform Cartopy, which is the extent of the GOES-R image. And according to the GOES-R documentation available at this link, the extent of the data is calculated by multiplying half of the full disk, the number of pixels of half of the full disk, by the pixel size in radians. This is complicated, right? But fortunately, this multiplication here is also available in the metadata, right? So you just need to get the result of this information from the metadata and multiply by the satellite height. It's also available in the metadata. And that's what we are doing here. And we need to calculate this extent 4 times, from the center to the east, to the west, to the north, and to the south. And uh, for that, we will consider the minimum axis, the maximum axis, the minimum y, and the maximum y, right? X and y is this multiplication, number of pixels by the pixel size, right? Um, this is a little bit complicated at first, but in the end, we need to do that because independent of the domain, either full disks or conos or mesoscales, by doing that, reading the information from the metadata, Cartopy will be able to position the map independent of the scanning mode. And and we will use the same instructions, right? So you will be able to just copy these informations and paste them in your own scripts and it will work, okay? The only thing you need to understand is that we are calculating this extent as required by Cartopy by following the procedure available in the GOZAR documentation. And at the end, we will get this list of four big numbers, right? And this list, I have called it here image extent. And in the imshow command, we use this extent as a parameter, okay? And this is your full script by now and the resulting plot. First, we have the instructions for data reading and manipulation, right? We read the netcdf file with the dataset command. We read the CMI pixel values, convert it to Celsius. Then in the plot configuration, we configure the size of our plot, we declare the projection of our data, we calculate the extent, add country borders, the states, coastlines, and grid lines, plot the image with the color map we want, with the minimums and maximums we want, add a color bar, the title. So this is the basic structure of most of the scripts you will see for GOZAR, and we will get this beautiful image here. Okay, now let's go to our Colab notebook again. Let me run these cells in a sequence to calculate the extent. And this is the image. Let me just demonstrate how you may change some colors, for example. I will set the country borders as light blue, the US states as light green, for example, the coastlines as light red, and the grid lines as gold, and run the script again. I'm just making some quick changes for you to understand how configurable this is. And I got an error, light red. Oh, it is a typo. I forgot to add a T here, right? Another error, light red is not a valid color. Let us check. Python named colors, list of named colors. I don't have light red. I have, let's see, light coral, for example. Let us put there. And here we have the country borders as light blue, the US states as light green, the coastlines as light coral, as they call it, and the grid lines as gold. Okay? And what I did here was changing the edge color and the color parameters from the map elements provided by Cartopy. And I have used named colors, right? So if you search for Python named colors, this will be the first result. Okay? You may specify colors as RGB values or hexadecimal values or named colors, as I just did here. Okay? And that's it. You have total control of the information you are showing. And to finish, a final comment is that we can use the same instructions to plot images from any domain. Here on the left, you have a conus image, which is available every 5 minutes. And on the right, you have a mesoscale image. Cartopy, as you see here, you position the maps correctly because we are making these extent calculations using information available in the metadata. Okay? And if you enter that web page developed by Brian, you may copy any link from any domain for any date. If I select, for example, mesoscale for September 8th, 15 UTC, look at the amount of information you have. One mesoscale per minute. Okay? You may download it with Colab and process it the way you want. Now let's check here on Colab some minor changes for the Conos plot. Plotting the Conos image, um, and the first change, as you can see here at the file naming convention, is that we are reading a file for channel number 2, right? The 0.64 micron band. So considering that, you don't need to convert it to Celsius because the pixel unit is reflectance factor, which varies between 0 and 1. And that is why in my imshow command, I'm using V minimum as 0 and V maximum as 1. Okay. Also, I'm using the gray CMAP with a lowercase g and a. And if we look at the list of color maps, this gray color map starts with black for the lower values and white for the higher values. And that's because in visible channels, the higher reflectances are from clouds, and I want to see them as white, and lower reflectances in the surface, and I want to see it in tones of black. Okay. Um, have also changed the title Go 16 band 2.64 microns. And by the way, you can also read this information here, the band, the wavelength directly from the metadata. And you have how to do that in the reference slide deck that we have uploaded to the SCAD interface. Another thing we did just for demonstration purpose is that we are applying the so-called square root visible enhancement, which is totally optional, just to make the image, make it a better contrast in our final image. Um, and what we are doing here, we are taking the square root for each pixel, right? And this is called the square root visible enhancement. But in the end, this is just to exemplify that we can make any calculation we want. And in this example, we are using the NumPy library and the sqrt command, which is the square root of our data. And that is why you have a very nice contrast here. Okay, let me comment it and run it again. Let's check the result. We should have the same image, but the contrast will be a little bit different. Okay? And to comment a line, you just need to use this hashtag. So this is it. We have the same image, but the contrast is a little bit different. And for some applications, not applying this correction is good. And for some other applications, applying that correction is you have a good, better result. And here we have the mesoscale plot with Hurricane Idalia using the same instructions. Okay, you can clearly see the overshooting tops, and that's because this is a 500-meter band. Okay, and that's it. This is the short version of this Colab notebook. Uh, and if you have made a copy, you may change anything you want. You may, for example, create a code cell, download other data, other bands from other times and dates using as a reference that graphical interface I have just um, referenced here in this code cell. Okay, you may change um, the color scales, you may change the colors of each Car2P element, and so on. And in the end of this notebook, let me open the table of content here. In the end, we have a link for the long version of this notebook with many more examples, right? More than 30 scripts for your reference, showing how to make a variety of operations like reading a shapefile, overlaying this is a shapefile with all the states and provinces of the world, how to overlay GLM data here, how to create RGB composites like the Hermes RGB, how to download data directly from the cloud using scripts without the need of manually inserting the links. You just have a variable here with the year, month, date, year and minute, hour, minute, and the band. And it will download and process this information. Okay? How to crop a full disk image, how to reproject the data from the original ghost projection to the equidistant projection, for example, and so on. So this is available for your future reference. And here on this slide, you have links for other notebooks. Apart from the known version of the notebook we have studied today, there is another one showing how to process numerical weather prediction data and how to overlay it with ghost images. Um, you have another one showing how to process oceanography products. Another one with miscellaneous products like total precipitable water, vegetation products, hotspots, and much, much more. In the end, you see that independent of the product, the instructions are very, very similar. Importing the libraries, reading and manipulating the data, configuring the plot, cartopy, etc. And finally, generating an image. Also, in our SCAD webpage, you have other slide decks apart from this one. And this one here, main slide from the recording, is the one I have used today. Okay? And the one I recommend the most is this one. Those are data processing with Python, with many, many slides explaining each instruction of the longer version of this notebook. Also, if you want to process data locally in your own computers, offline, you have this procedure here, which will show you how to get started. Another nice reference is this one, Introduction to Visual Studio Code, where you see how to use this very nice programming interface to write and run your scripts. And if you want to learn Python from zero, here we have added some ebooks that are available for free, distributed free of charge by the authors. And these are great resources. And we will learn concepts from the very basics like loops, variable types, functions, dictionaries, and so on. And that's it. Now, Marcial will make another presentation covering additional aspects of the GOZAR data processing, visualization, and analysis with Google Colab. Thank you very much.